So in class on Wednesday, I said, let's determine what did I? Oh, determine the plane or specify the plane, which is determined by the following 3 points. So here are the 3 points. Point, let's call them U. These are the ones I gave in class. Right. Okay. So V and W. Like that. 3 points determine a plane. Right? True, false, yes, no. So 3 points determine a plane. And I said the most basic sort of strategy would be to do the following. Would be to remember that any plane can be given by this equation. A lot of times people will say A, they won't say ABB, they'll say ABC, and they'll put a D there, but you can divide by D, and then you would have a constant. So you might as well write it like that, it makes things easier. So how do you determine A, B, and C? Well, you plug in these points and solve the system. So I want to do that. And the reason I really want to do that is because a student in the class noticed a problem. And kudos to you for noticing this and doing that. So let's go ahead and do this. So let's start with the first point. So we put a 1 in for x, from x, y, z. So for x. So you get A, 0 for B, C we get 2, so plus, or Z, I'm sorry, 2C equals 1. Now from this point right here, we don't get an A, we get a B. And then we get 3C. Okay, and finally from the last one we would get negative 2A, let's see, plus 3B plus 5C. Sorry, that equals 1, and that equals 1. So here is our system of equations, and we want to solve it. And I said in this course here, I don't care how you solve it, but I'm just going to solve it. How should I solve it here? I'll solve it by the elimination method. I'm sure you remember that. Probably done it a whole bunch of times in your life. So let's leave the first two equations alone. And look at the third one. How about if I add 2 times this? So I'm going to take this row and add 2 times this row. Now what will that do? That'll get rid of the A's. I got to remember here I'm going to add, because I'm going to shortcut, not write everything down. I want to add 2 times this row to this row. So that'll be gone. 2 times that, there's nothing there. So that stays the same. 2 times this is 4, plus 5 is 9. And 2 times this is 2, plus 1 is 3. So there's our system. And I'm trying to get this in, if you recall, it's called echelon form, but we're trying to get this in this diagonal form. So how about if we, first off, just to simplify things, let's divide this row by 3. That would give you 1, a 3, and a 1. And maybe at this point you notice something, or you should notice something. And you should say, wait a minute, wait, hold on a second. These two equations are the same. They are the same equation. If you have 2 equations which are the same, you can erase one of them without, you're not losing anything, they're the same. So this system is equivalent to this system. The original system I wrote down is equivalent to this system. Now, if you think about it for a minute, what's going on here? This is a plane, this is a plane. We have 2 planes. Where's a piece of paper when I need one here? Hold on. I want to grab a couple of planes here is what I want to do. Here's a plane. Right there. There's a plane. Here's another plane. 2 of them. Not 3. 2. Thought we had 3, but turns out 2 of them are the same. So if you have 2 planes, how do they intersect? They intersect along a line. If it was 3, it was a point. Now if it was 3, which you would almost always expect to have, almost always. If you write down 3 random planes, almost always they'll intersect at a point. One uniquely determined point. That would be the point ABC, and that would be what we're looking for. I didn't plan this, but as it turns out, this initial problem didn't determine 3 planes, it determined 2. 2 intersect along a line. They intersect along a line, not a point. And that means there's no uniquely determined equation here. There's an infinite number of solutions. What does it really mean? These 3 points, which I swear to you, I testify, I chose randomly. I just, I don't know, what are nice numbers? I don't know, 1, 0, 2, 0, 1, 3, whatever. They're nice, easy, crispy, single-digit whole numbers. I just so happened to pick 3 points which lie in a line in 3-dimensional space. Now, if you think about it, if you could create a hologram and we blindfolded you and spun you around and we said, snap your fingers in 3 random places, what do you think the odds are that those 3 points would exactly follow along the line? Well, the answer is basically they won't, or the probability is so low it's not worth talking about. Actually, mathematically, the probability is 0, but let's just say if they're truly random, but you're human, so you don't truly do random things, it's very, very low. So what I want to do is demonstrate that these 3 really do fall along a straight line. And I want to do it using the method of vector representation of a straight line that we talked about in class. Consider these 3 points. Let's just take a look at the first 2, and let's find the vector that goes between u and v. What is the vector that goes between u and v? Well, we can look at v minus u. That is a vector that goes from u to v. And how do we do that? We just simply subtract. So 0 minus 1 is negative 1, and 1 minus 0 is 1. And and 3 minus 2 is 1, like that. So there is our direction vector. That's the vector that goes between u and v. And how do we write the line? Well, we write it like this. We can write it one of 2 ways, but I'll write it like this right now. Negative 1, 1 times a parameter t plus a point on the line. So I think I talked about this before. This is very analogous to y equals mx plus b. But here we have a direction vector that really is, the analogy to that is the slope of a line. And the y-intercept, we don't really have a y-intercept here, but we have a point on the line. What's a convenient point on the line? How about if I just use this point right here, 1, 0, 2. So the point 1, 0, 2. So if you look at the set of vectors generated by this expression after substituting all real numbers in for t, you would get that straight line. Now, what I claimed a minute ago is these 3 points are on the same line, or they lie along a line. How would I prove that? Well, these 2 are on the line by the way I created this line. The question is W actually on this line? How do we find out? Well, let's see. If I multiply this out, look, here's the x coordinate, 1 minus t. That would give you the x coordinate. Here, I'll write it like this. X. 0 plus 1 times t, that would be t. That would give me the y coordinate. And 2 plus t, that would give me the z coordinate. Now, if this point is on this line, there should be some value of t that will generate x, y, and z to satisfy this. So let's see if we can actually do that. What is x? Negative 2. What is y? 3. Or what would we like it to be? 3. And z is 5. From this we get t has to be 3. Put a 3 in here. Lo and behold, check. Put a 3 in here. Lo and behold, check. So what happened was I gave you 3 random points, or at least random to the way my head was thinking. 3 random points in 3-dimensional space. And in a nearly miraculous way, I gave you 3 points that lay on a straight line. So this is a special case that could happen. Freaky case, weird case, unusual case, hard to believe case. But there it actually happened. I don't think that's ever happened before, and I don't imagine it'll ever happen again. So there you have it. Witness to history, and I will see you all Monday online.